What we're going to begin covering today is more AP Computer Science principles material that could show up on the multiple choice portion, and that would be talking about data and where data is stored, how data is stored as well. But before that, I thought it might be nice to give you guys some background knowledge about computers in general. That way, when we talk about data, you know exactly how and when it's applied. In this PowerPoint, there's going to be a lot of information that is not going to be tested on the AP test, but there is also some information that will be. So I'll be sure to denote what is fair game and what you're not expected to know. But like I said, a lot of this is just background information for you guys to hopefully, just so that you guys can understand it a little bit more and why we need to know certain things. So today, what we're going to be covering for the first PowerPoint is what exactly is a computer, the various parts of a computer. Obviously, we're not going to go too in detail because I would say some things that you should know. Maybe what's a computer? What is this? You should know that for the AP test. The different parts of the computer you do not need to know for the AP test. And then this right here and this right here will be important for the AP test, but not super important. It is fair game, however. So let's talk about what is a computer. So a computer, by definition, it is just electronic device that processes data according to a set of instructions or commands. So your laptop, your desktop setup, that's a computer. It's exactly what you expect it to be. However, some people don't understand the difference between software and hardware. Computer is perfectly understandable for many, but let's talk about the difference between hardware and software. So first of all, software, so you do need to know, whoops, it's like I accidentally ended my PowerPoint. So for, hang on here. Yeah, I don't know. So for software, it's programs and other operating information used by a computer. So not tangible, hence the word software. It's pretty much any program that can run on a computer. That is what a software is. It's not something that you can physically touch. So we will be talking about this a little bit more in the PowerPoint, but some very common examples would be like your operating system. How is your computer able to run? Or even just something that you download in order to use, Microsoft Word, or maybe even and Zoom would be a software. So like these are various programs that are used by your computer. Hardware refers to the physical components that a computer is made of. So the things that are physically in your computer, that would be hardware. So these are tangible as opposed to software. So there's two categories of hardware, core and peripheral. Core is what we're going to be talking about in the next part of our PowerPoint. Core is like literally physically in your computer, whereas peripheral is not, it's connected to your computer, but it's not necessarily part of your computer. So for example, like a printer would be considered a peripheral hardware. It's not physically part of your computer, but is a hardware that your computer can utilize. Another thing that I want to mention about hardware is that computer is not one individual device. It is made up of different modules that work together. These different components are hardware. So the various, if you were to open up your computer and look, there are very different parts to your computer. For example, like a USB port, how it's able to read that kind of information. So that physically is not your computer, but it works with your computer and is still hardware. All right, let's talk a little bit more about the computer. So this part, like I said, this right here is fair game in terms of the difference between, you need to know what software is for the AP Computer Science Principle Test. You have to know. But the next slide, parts of a computer you do not need to know, and I'm just only talking about it just so that you guys have a little bit of background as to how a computer works. And eventually, maybe you, or hopefully, you should be able to apply that to the data that we're going to be talking about. So parts of it, there's different parts of a computer. The main parts, first of all, we have our CPU, our central processing unit, our main memory, secondary storage devices, and our input and output devices. Once again, there's so much more that goes into a computer, but we're not going to dwell too much on this. It's not part of the AP test, but we're just going to talk about it a little bit more about these 5 things in a little bit more detail for today. The first thing we're talking about is a central processing unit. So in the central processing unit, we have our, it's pretty much the brain of your computer. If you don't have a CPU, or your computer cannot operate because it cannot execute instructions. It cannot complete the tasks that you want it to. So literally, if you want to think of a CPU, you could think of it as the brain. It takes instructions from the main memory. If you look in the previous slide, we do have our main memory right here. It takes instructions from the main memory, it executes it, and then it produces any data or any output that is required. That will be sent back to the main memory. So there is some like a relationship like this going on in our computer. There are 2 components for the CPU. We have our control unit and our arithmetic and logic unit. So the arithmetic and logic unit is kind of like a calculator. It's not really a calculator, but it does all of the computation. Whereas the control unit doesn't do any computation. It will provide instruction, or it's like a guide. If I were to give an analogy, it's kind of like a conductor in an orchestra. The conductor isn't actually playing an instrument, however, it is guiding. It is allowing everything to work harmoniously. So that is what the control unit does, as opposed to the arithmetic and logic unit. Going back, or just going a little bit further, how a CPU works. First of all, it fetches the instruction from the main memory. So how main memory is actually, I think I talk about this later. We'll talk about how the main memory is set up, but it'll fetch the instruction from the main memory, which means it has to know exactly where to get the main memory, or get the data from the main memory. Then it has to decode and generate an electronic signal. So this is decoding the instruction. So the instruction that the CPU gets, it has to be decoded. Then that instruction will be executed, and then it will be output. So here, this is the instruction from the main memory. It is input into the CPU. So this entire thing is a CPU. We will talk a little bit in a little bit more. We'll talk in a little bit more detail how to find a specific instruction in main memory. The instruction is then decoded and executed in the CPU. And then the result is outputted from the CPU and returned back to the main memory. So it seems like a lot. Don't worry, you don't need to know this much detail. The reason why I want to introduce this to you is so that you guys can see how your computer works. Your computer is heavily reliant on the brain, the CPU, which needs to work with the main memory. So that's all you guys need to know for now. The next part we're going to talk about is the main memory, since we finished talking about the CPU. So the main memory also is known as the random access memory, or RAM. Hopefully you guys have seen RAM in here or there. This is volatile. Volatile means that it requires power to retain whatever information or data. So if you were to unplug your computer, or if your computer loses a power source, then your main memory will be wiped. It will start off with a clean slate. This is not to be confused with the secondary storage devices. So a lot of people are, they are a little bit confused when they think main memory. They think of main memory being your, like where you save your files, where you save like your documents. That's not main memory. That goes under secondary storage devices, which is going to be the next thing that we're talking about. Main memory is what is used to work with the CPU. So what instruction needs to be run next, or temporary storage for your CPU to run. So that's the reason why when your computer stops running, or like when you unplug your computer, or when there's no power source, you should not have any files saved on the main memory. They should be in the secondary storage devices. That is where you can continue to access. That is non-volatile, because even if you were to take out the power from your laptop or your computer, it'll still be saved there. The next thing I want to talk about main memory is that we have 8 switches, or what we call bits. This is what stores the data in your main memory, and not just the main memory, even in the secondary storage devices. We'll talk about why we could call them switches, but the formal term is bits, which is short for binary digits. Keep this in mind, because we will be going back to this. Data in computers is not stored as you see it. So for example, this word right here, main memory, in my computer, it's not stored as MAIN space MEMORY. Instead, it is stored as a binary encoding. So a whole bunch of zeros and ones. Binary just means zeros and ones. And that's how it's stored in our computer. Computers, unfortunately, can only understand zeros and ones. If you were to go very deep into what, I guess, the program or what your computer can actually see, just zeros and ones. A little bit further, these 8 bits or 8 switches create what we call a byte. And we will also go into this in a little bit more detail as we go along, but that's where your kilobyte, megabyte, gigabyte, terabyte, that's where all of that comes into play. So this is going to be our primary focus for today, and also next week as well, when we're talking about memory, how things are stored, and the encoding of various data. And this is literally the reason why I'm introducing all this to you. But since we're still talking about it, we could talk about the secondary storage devices as well. So the secondary storage devices can hold data for long periods of time, even when there's no power. So this is non-volatile. Examples of secondary storage would be a USB, like a flash drive, your actual disk drive, so like your actual hard drive, what your files are stored on in your computer or in your desktop. And then also the solid state drives, which, do I have one? I do not have one in front of me right now, but so like kind of like a portable hard drive, and I guess it would be another way to say solid state drives. So those things that you actually store your files on is typically what we call secondary storage. Just once again, to really emphasize the difference between main memory and secondary storage. Main memory is volatile. That's the big thing, whereas secondary storage is non-volatile. Main memory is very, very expensive. I mean, that's the thing that your CPU interacts with in order to operate, because it needs to know what exactly to do. Whereas secondary storage is cheaper, as like you could probably go on Amazon, buy a USB drive for like depending on what size, something like $15 to like $70, depending on the size. Main memory is faster data access, because it's literally like with your CPU, it's interacting directly with the CPU, whereas secondary storage is slower, because secondary storage actually has to work with the main memory. So the main memory goes straight to CPU, whereas a secondary storage goes to main memory, then to CPU. So it's a little bit slower. Main memory is limited capacity because it is more expensive. You can't afford a very large main memory. Whereas secondary storage is much cheaper, so extended capacity. You could have like 2 terabytes of secondary storage, that'd be fine. Whereas main memory, you'll probably see is like 8 gigabytes. If you jack up your computer more, maybe 16 gigabytes or more. Main memory is directly accessible to the CPU. We just talked about that, whereas secondary storage is not directly accessible to CPU. It has to be copied to the main memory first, which is why it is slower. And actually, these two are the same thing. Data is lost when there is no power because it is volatile, whereas secondary storage is non-volatile. So data is not lost when there's no power. It's just sitting there waiting to be used whenever you decide to turn your computer on again. And the last thing I want to talk about are the input and output devices. So these are the things that you guys use in order to interact with your computer. So your keyboard, your mouse, these are input devices. Without them, you can't really interact with your computer. There's no way for you to provide additional information to your computer. For example, if you click on something, that provides additional information, or it's like a trigger to perform some kind of task. But if you don't have those input devices, then your computer is still a computer, but it doesn't have much to go off of. Examples of output devices would be like a screen or a monitor. So your computer is still a computer without a screen or without a monitor, something to display everything. However, it's nice to have your screen because you are able to see exactly what your computer is outputting, a visual representation of what your computer is outputting as well. So those are different input and output devices. Altogether, it makes a very nice computer that you can use. So we just talked about all of this. Let's go ahead and just delve into a little bit of software. So we finished talking about the computer already. Once again, that's not going to be part of the AP Computer Science Principles test. However, what is going to be the memory, how data is encoded. But we'll get into much more detail in a moment. Don't worry. And then we have our software. So software, once again, is the programs and other operating information used by a computer. Let's delve into it. There's two types of software. So once again, we're going back into the realm of the AP Computer Science Principles test. So you do need to know this. There's two types of software. We have our operating system, and then we have application software. So the operating system, it is the visual representation of your computer. I would say this is the important thing. So Windows 7, Windows 8, Windows 10, those are operating systems. If you are using Mac, then you have your Mac operating system. I don't even remember what the newest one is called, but is it, oh, Catalina. That would be an operating system. If you're using Linux, that's an operating system as well. This is what manages your computer hardware and the processes. So this is what works the closest to your computer. Without an operating system, you just kind of have a computer and you're not really able to visualize or interact with your computer unless you're very well versed, unless you're like well versed in computers. But I'm assuming most of you guys have an operating system with your computer. That way you can use it effectively. Then we have our application software. Application software is just any software that is not an operating system. So Microsoft PowerPoint, Microsoft Word, Google Chrome. I guess another one I have is Adobe Photoshop, Zoom. All of these softwares that are not your operating system are considered application software. So know the difference between operating system and your application software. Let's go into another subset of, I guess not really a subset, but something that you guys should also need to know. What is a program? A program is a set of instructions that enable the computer to solve a problem or perform a task. You guys, hopefully, as long as you're doing the homework, have created multiple programs already. It's when you create a set of instructions that enable the computer to solve a problem or perform a task. If you tell your computer, print hello world, that is a computer program. You wrote an instruction that performs a task. Collectively, if you create a program and you create with like a set of instructions that perform something, you could also call this an algorithm. So a computer program is a little bit more, if a lot of people, there's no formal definition for an algorithm. What makes something an algorithm, unfortunately. I could do my best to define it for you, and I did last week when we talked about algorithms. However, it is heavily debated what makes a computer program an algorithm and what does not, or what is not an algorithm. So that's like a little bit of the iffy thing, especially when you get into academia and like the higher, like a master's program or a PhD program. But best definition that I could give to you guys, I gave to you guys last week. And again, the collection of these instructions where you are performing some kind of task is called an algorithm. So within a program, you could have multiple algorithms where you have a collection of instructions that are performing a task after a series of algorithms, or your computer program can be one algorithm. You could actually make our software. So software is made of programs, or at least one program. So software, we have our software, and then we have our programs. And within our programs, we can have algorithms. And then within algorithms, you have instructions, I guess. That's something I might want to add. Instructions. Sorry, it might be a little bit difficult to read. We talked about algorithms, but once again, I want to define it for you. A set of well-defined steps for performing a task or solving a problem. These steps must be sequential, not to be confused with pseudocode. So here and there, you guys might have heard me talk about pseudocode, but today I'm going to define pseudocode. It's an informal, high-level description of the actions of a computer program or other algorithm. So it's a way for you to represent an algorithm that is like code. It resembles code. But it doesn't actually, it's not actually code. A lot of the time in the homeworks and also in the quiz that you guys will be getting soon, pseudocode is it's not going to mirror a specific coding language. However, as long as you understand the basics of programming syntax, you should be able to decipher what the pseudocode is trying to have you do. So as an example, we have our algorithm here versus pseudocode here. So the algorithm is just a step-by-step series of instructions. We have the variable a starts with the value 10. That would be step number 1. Whereas in our pseudocode, we have 1, set a to 10. That's a little bit more pseudocode because it is, or we could have just said like something like a to 10, or we could have said a is equal to 10. There's various ways for you to write pseudocode, but as long as it's somewhat mirroring how code should look like, and it is still following the step-by-step instructions for the algorithm, you have your pseudocode. Another step for this step 2 for the algorithm, the variable 2 starts with the value, the variable b starts with the value 2. So that would mirror this step 2. I'm going to go ahead and go to step 4 actually. Skip over to step 4, which is store the value of a times b in a. So we have our step 4 here, set a to b times a, which is exactly what we have here, except written in a little bit more coding format. It's not exactly coding format. It doesn't mimic a specific syntax for one programming language, but remember, pseudocode, it's not actually supposed to be following one programming language. Some commonly used programming languages, we have Python that you guys learned. If I know a lot of you guys are learning JavaScript, you guys are If you're going to take AP Computer Science A, you will be learning Java. Some of you guys probably already learned C#. C++ is my personal favorite. It is a little bit more of a lower level language as opposed to higher level language. Lower level language just means it works more with the hardware, whereas a higher level language is further away and just more software. It's just more software, and it doesn't really work too much with machine language. So C++ is one of the languages that are closer to lower level. It's not a lower level programming language, but it's closer to a lower level programming language. So when I say lower level programming language, when I say lower level, I don't mean it's easy. I don't mean like the level of like to learn it is easier. It means it is more similar, more machine language. So what the computer would use to perform instructions, whereas a higher level programming language doesn't mean that it's more difficult per se. It just means that it is something that normal programmers use to instruct a computer. Programmer uses to instruct computer. So these are all high level languages. It's just that C++ is closer to a lower level language than like let's say Python or Java. Sorry, this is from last year's PowerPoint. We're gonna be using Python. Common elements in every programming language regardless is keywords, operators, punctuation, programmer defined names, and syntax. So you guys should recognize these operators: plus, minus, divides, multiplication. We even had like the less than or greater than, less than or equal to, equal to. These are all operators. Punctuation, we don't have semicolons in Python. We have semicolons in other languages like Java and C++. But remember, we did have like colons, for example, like if and then condition colon. We did have punctuation. Programmer defined names, variables are extremely important in every coding language that allows you to store. It's an abstraction. That way you're able to understand what a specific list is, or you could label it. We have keywords, int, double. Double is something more for C++ and Java, but we use float, str. Those are all words that you cannot reuse because they're reserved for specific purposes in each programming language. And then we have syntax. If instead of writing x is equal to 3, if I write 3 is equal to x, Python would understand this, what exactly x is equal to 3 is, but just by switching the order in which Python expects, this can confuse Python. So all of these various components are in every single programming language. So I thought I'd just close off today, or not today's class, but close off this like little review / background information by giving you guys a multiple choice question. So these are grammar rules, or what are these are? These are grammar rules that must be followed when writing a program. So let's see. Let me make it a poll.
I always do something different.
All right, go on ahead. What are the grammar rules that must be followed to when you write a program? Okay, I'm gonna give you like 5 more seconds. So yes, the answer is A. These are the grammar rules. So remember I said like X is equal to 3 versus 3 is equal to X. It's not really grammar. That's the reason why we have the quotation marks. But we have X is equal to 3 is our, like that would be the correct way to write it. So this would be this is what we call our syntax rule. That has to be followed when we're writing a programming language. Otherwise, whatever our compiler is or whatever our interpreter is will not understand what we wrote. Okay, that being said, we're gonna move on into our actual PowerPoint for today, which is on oops, representing and transmitting information. Okay. So in the last PowerPoint, I mentioned this. So in random access memory, how information or data is stored is 8 switches, or what we call bits, or pretty much bits is short for binary digits. From now on, never call it switches. You guys are going to call it a bits or binary digits, but you might as well call it a bit because it is much shorter than binary digits. And I also mentioned that 8 bits makes up a byte, and each byte is an address. So this as well is going to be important. Remember this. This is pretty much like, I could almost always guarantee that a question in this form is going to show up on the multiple choice portion of your test. Um, 1 second. There we go. Okay. So let's talk about what binary numbers are. So binary numbers are numbers expressed in a base 2 numerical system, which only uses 2 symbols, 0 and 1. If you've never heard of binary numbers, this sounds like complete gibberish to you. So let me do my best to explain. Numbers have different systems. We use a decimal system. We use, what we call a decimal system, or what we call base 10. The reason why it's called a base 10 system is because if we count the numbers that we use, like the actual digits that we use, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are the actual digits that we use. If we count the numbers of digits that we have, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 total digits that we have. We do have more numbers, but those numbers are made up of these digits. 10 digits in total. So in a base 2 numerical system, we only have digits 0 and 1 because there's literally only 2 digits in a binary system. Which presents another challenge. You are used to counting up to 10 and then going to 11, 12, 13. So how can you represent So it's like 0 would obviously be 0, I guess. So like 0 is the same thing as 0, regardless if you're in the decimal system or in the binary system. 1 could easily be 1 in either system, but how would you represent 2 in the binary system when the number 2 doesn't exist in the binary system, because you could only use 0 and 1. So that's the challenge that we are going to have to face, and that I'm going to try to train you guys to overcome in this PowerPoint. Let's first of all start by understanding how counting works. This is going to sound like we're in kindergarten again, but let's start by figuring out counting. So when we count in decimal system, the way that we normally count, we start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Actually, let's start with 9, I guess. We'll stop at 9. So we got to 9. We have maxed out all of the digits. We used all of the digits that are available to us, 0 through 9. So what do? You reset the ones position and increment the next position, the tens digit. Then you keep going because you reset the ones place. So 11, 12, 13, 14, 15, 16, 17, 18, 19. You've maxed out the ones place again, but it's okay, because what you can do is reset the ones place and increment the tens place. Then you keep going, 21, 22, 23, 24, 25, 26, 27, 28, 29. You've maxed out the ones place again, but it's okay because you can increment the next place value. So it's 3, 0, and then you can keep going. Let's say you get up to 90, 91, 92, 93, 94, 95, 96, 97, 98, 99. So what you can do when you get to 99 is, it's fine, reset the ones place, so it's a 0. You increment the next position over, which is this 9, the tens place, but that maxes out too, because you've already reached the maximum digit 9. But that's okay, because we can reset that place value and increment the place value over. So now you have 1, 0, 0. Let's see how that translates in our binary system. So in our binary system, we can start with 0. So the 0, 1, 2, 3, 4, 5, 6, 7, 8. When we start with our 0, so this is decimal, and this is going to be binary. Binary, decimal 0 and binary 0 are both the same. They're both 0. Decimal 1 and binary 1 is the same. Here's where it gets tricky now. In terms of place values, I was in the rightmost place value for this. But when I add 1, when I try to increment this one, I max out. I reach the highest possible number that I can get in the binary system. Because remember, in binary, I only have 2 digits, 0 and 1. So I reset that place value to 0, and then I increment the next place value. Does that make sense to everyone? Once again, 1 is the highest digit that I can attain in a binary number. So when I try to add 1 to this number, I have to reset the place value to 0 and then increment the next place value. When I try to figure out what 3 is, I add 1 to this, which is perfectly fine because I would just get 1, 1. because 1 plus 0 is 1. 1 is a perfectly normal digit in a binary number. Then I go to the number 4. If I add 1 to this, I have an issue. The issue is that I've already attained the largest possible digit that I can here. So I reset that place value to 0, and I increment the next digit, but the next digit is already a 1. So I've maxed out in that number. So this also is going to be a 0. We reset that digit and increment the next place value. So it's a 1. So a 4 in decimal is a 100 in binary. When we take a look at 5, when we add 1 to 5, that's perfectly fine because that's 1, 0, 1. Nothing crazy going on there. When I add 1 to 1, 0, 1, however, I face the issue that there's already a 1 here. So that must mean that I have to reset and increment. So I reset the rightmost place value to 0, increment the next place value, which is perfectly fine because it's 0 at the moment. So 0 plus 1 is 1, legal in the binary system. And then I have a 1 here. So a 6 is 1, 1, 0. Then when I try to figure out what 7 is, 7, we just add 1 to it. That must be 1, 1, 1, because when we add a 1 to, oops, that's a 1. When we try to add 1, that works out perfectly fine. Here's a tricky one, whatever 8 is. When we try to add 1 to our 7, we face the issue that our 1's place, so the rightmost digit, is a 1 already, which is the largest possible digit we have. So we want to reset this, or because of this one, we're going to reset it to a 0, increment the next number over, but this is also a 1. So when we try to increment it, we've already maxed out, reset it to a 0, and increment the next one. When we take a look at this number right here, it's already a 1. So we have to reset it to a 0 again because that one has maxed out. Then increment the next digit over, and we put that as a 1. So as you can see, our number system here is for binary is completely different and a little bit I mean, hopefully it makes sense, but it's very counterintuitive to what you guys have known for the last, I don't know how old you guys are, but like the last like 15 years of your life, maybe on average. I don't know how you guys are, but you guys have grown up thinking about 0 through 9 being the only digits that you need to really care about. But in binary, it's just 0 and 1. And because of that, the number of place values that you have will grow very, very quickly. The reason why binary numbers are so important in computer science is because your computer can only understand 1s and 0s. And most of this is due to the logic of 1s and 0s. When we talked about conditional statements with ands and ors and not, there was only true and false. And the way true and false is laid out, you only have 2 options, is analogous to the digits of binary numbers, 1s and 0s. So binary numbers can be easily translated to logic just because of the fact that there's 1s, which represent true, and false, which is like our 0s. So binary numbers are imperative to data encoding and decoding in computers, and also like information that is being stored in a computer. We'll talk a little bit more about how exactly that works, but first of all, you guys probably want to know, what is the shortcut to converting binary numbers to decimal numbers and decimal numbers to binary numbers. Because the way that I just showed you guys, converting decimal numbers to binary numbers was, I don't want to say complex, but it was a process. We started from 0 and we continued to add one, add one, add one, add one. And that's how we got up to the number 8. But let's say I gave you the number 57. You probably don't want to do this process up to the number 57 because it's terrible. So that would be so much paper that you would have to use. So let's go ahead and talk about how it would work. In this case, as we talk about right here, in order to switch between the binary and decimal systems, we would have to use algebra. And this is where the math is going to come in. Hopefully you guys have a piece of paper and like a pencil to write with. That way you guys could hopefully follow along. So let's talk about the powers of 2. So the power, like binary is in terms of 2 digits, 0 and 1. So what we can use in order to convert between binary and decimal to binary is, or actually specifically binary to decimal, or sorry, binary to decimal. Use this for binary to decimal. Binary to decimal. We want to use powers of 2 to convert binary numbers to decimal numbers because we already know that this is a base 2 system. A base 2 system that we could take advantage of by using every single digit. So for example, if I have 10011101, just as a pure example, this 1 is in like the ones place for is in the ones place. This 0 is in the twos place. This one is in the fours place. If I were to give an example, so like an analogy, let's say I have a decimal number, 56,342. This 2 is in the ones place. This 4 is in the tens place. This 3 is in the hundreds place. This 6 is in the thousands place. This 5 is in the 10,000s place, which if we were to write in exponential terms, this 1 is in the 10 to the 0 spot. This 10 is in the 10 to the first spot. This is 10 to the second power, 10 to the third power, and 10 to the fourth power. But we're dealing with binary numbers right now. So instead of using 10 to the 0th power, 10 to the first power, 10 to the second power, 10 to the third power, we are using 2 to the 0 power, 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power, 2 to the fifth power, 2 to the sixth power, 2 to the seventh power, 2 to the eighth, 2 to the ninth, and 2 to the 10th power. So each of these digits represent, or each of these digits are in a different place value. Starting from the right-hand side is the smallest. And as you go towards the left, the place value will increase by a power, or by a factor of 2. So here we have, this is 2 to the 0th power, the first or the ones place value. This is 2 to the first power, which is like the twos place value, the fours place value, the 8th place value, 16th place value. And the reason why, once again, this is different is because this is a binary number, a base 2 number where you can only use zeros and ones, as opposed to a decimal number where you have 10 total digits that you have at your disposal. So that's the reason why you have 10 to the 0, 10 to the first, 10 to the second, 10 to the third, 10 to the fourth. They're not so different in terms of the structure, but the meaning behind it, the numbers, the actual numbering system behind it is very different. But the idea still translates between the two number systems. So if we wanted to convert one number into the other, you need to first of all understand their place values. And then you need to figure out how exactly or what exactly that number would be. When I expand my number for decimal, if I expand it, this is exactly the same thing as 5 times 10 to the fourth. That's because the 5 is in the 10 to the fourth place value, plus, maybe a different color, plus 6 times 10 to the third power. Ooh, that's a little bit hard to see. Plus 3 times 10 to the second power, plus 4 times 10 to the first power, plus 2 times 10 to the 0th power. That's how you could expand that number. And these two will be exactly equivalent. So we could also use this idea and translate it so that we can convert one number into another. So let's try this example. We're going to change the following binary numbers to decimal. When we do this, this place value versus this place value, remember, start, find, what's going on here? Find place values starting from the right. So this is 2 to the 0th power, then 2 to the first power. Then expand the number by multiplying digit to place value. Find the total sum. So this would be 1 times 2 to the first power plus 0 times 2 to the 0th power. The 1 comes from this place or that digit with its respective place value, whereas the 0 times 2 to the 0 power comes from the digit and its respective place value. And this will give us 1 times 2 plus 0, which is the same thing as 2. So 1, 0 in binary is the same thing as 2 as a decimal number. Another thing I want to also mention is how things are written. So sometimes if you precede the number 1, 0, 1, 1, just like that, is it a binary number or is it a decimal number? Because remember, in a decimal number, 1 and 0 are also valid numbers. So to clarify that, you'll often see parentheses around the number and then a number, like a subscript under it. This is what we call the radix, or in what we say, the base. So this must be a base 2 number. The leftmost number represents the most significant bit, and the rightmost number is what we call the least significant bit. And as you can see, this is exactly what we just talked about. We have our place values. 2 to the 0 is the rightmost number, so it's this one right here. So this one is our rightmost number, so this is what we have. We have our number after that, and that would be this number. So 1 times 2 to the first power. Then we have our next number is 0, 0 times 2 to the second power, because that is the corresponding place value and the digit being multiplied with it. And in terms of our most significant bit, that 1, that is being multiplied by 2 to the third power, which is the correct place value. So let's keep going from what we have here. I'm going to edit this so that instead of just saying 2, we can clarify that this is 2 with a base of 10, so a radix of 10. It is a decimal number, so it's a base 10 number as opposed to 1, 0 earlier, which was supposed to be a binary number or a base 2 number. So this is our base 2 number once again, and then hopefully we'll just have time to finish this one example. When I rewrite my number, so 1 0 1 0 1 0 1 0, start from the very right hand side and figure out the place value. This is 2 to the 0 power, 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power, 2 to the fifth power, 2 to the sixth power, and then 2 to the seventh power. Then we're going to expand the number by multiplying the digit to the place value and finding the total sum. So I have 1 times 2 to the seventh power plus, I'm just going to ignore this one because we know that 0 times anything is equal to 0. So we're kind of wasting our time by even considering what the calculation for 2 to the sixth power is. I'm going to go to the next one, which is 1 times 2 to the fifth power. Ignore this one because we have 0 times 2 to the fourth power and 0 times anything is 0. 1 times, plus 1 times 2 to the third power. Ignore this one because it's 0. Plus 1 times 2 to the first power, this one over here. And we can ignore the last one. Figuring out exactly what is, or not, we just have to calculate and then figure out what these numbers come out to be. 2 to the seventh power, I believe, is 128 plus 32 plus 8 plus 2, so 40, 130. So this is 170 as a decimal number. Much better than counting from 0 and then incrementing our way up all the way to 1. Hopefully, I hope you guys see that. So this is what we're going to be doing in order to convert decimal numbers to binary numbers, or sorry, binary numbers to decimal numbers. When we see binary numbers, it has almost no meaning to us. When you see 10 10 10 10, you have no idea what that means. But when you convert it into a decimal number, you have a better understanding of what it is supposed to represent. So it is of importance to understand how to convert binary numbers to decimal numbers. Unfortunately, we don't have the time to learn how to apply it for today, but we will pick up where we left, or we'll pick up from here next week, where we'll go into a little bit more detail. We'll learn how to convert decimal to binary. We will learn other number systems, hexadecimal and octal, and we will also apply what we learned to encode and decode data.